Okay, 6.3, multiplying vectors by scalars. Taking any type of vector that we know the direction for, and we can scale it bigger, or we can scale it smaller. Just multiply it by a number that isn't 1, and that's multiplying a vector by a scalar. Super easy. So we can multiply vector A by different values of k being any constant, so it doesn't really change the direction, just changes the scale. And it can affect the direction and magnitude of A. I want to speak a little bit on direction. All we can do is change the direction if we multiply by a negative. I can't change the direction, if that makes sense. Okay, I can't change the angle. I can only take this vector and multiply it by a negative value, and it goes in the opposite direction. So for instance, if this is vector A, if we want to come up with values for these ones, just to come up with them as examples, I can say, well, this is 2A. It looks like double. Sure, yeah, it's probably not double, but it doesn't really matter, just to make a point. This one is going in the opposite direction, so this is just negative A. So I multiplied it by -1. This is going in the opposite direction, looks smaller than A, so to make something up, I can say, well, this looks like -1/2 of A. Okay, so all I've done is I've taken the vector A, because the vector has direction, and I've just multiplied it by a scalar, changing its length and possibly its direction, going in the opposite direction. But just because I multiplied all of these by a number, these are still all collinear. Okay, they're all parallel. Okay, multiplying a vector by a scalar keeps it parallel, keeps it collinear. So it's something to really remember. Okay, we're going to talk about something in unit vectors. I have a little definition up there that makes more sense, but unit vectors are just vectors with the magnitude of 1. Really important, because we love multiplying by 1, and if a vector carries the information of a direction with it, and we're multiplying by 1, best case scenario. I can now multiply by 1, but also include the information of the direction. So vectors x and y are unit vectors, magnitude of 1. They make an angle of 30 with each other. There's x and y. Calculate the value of the magnitude of 2x minus y, and then find its direction. So first I'm going to find the magnitude. I drew the diagram, and I just played around with 2x. This is another x. And then instead of doing tail to tail with the minus, I'm like doing -y, So if I do 2x minus y, and I put them head to tail, this right here, this red one, is 2x minus y. Okay, so to find that, a few ways I can do it. I can transfer this 30 in here with Z pattern. Okay, and I have to find the red. I know that this length is 2 x's, and since they're unit vectors, it's really a 2. And this -y is a 1. Okay, so it's just a triangle with a 2, a 1, and a 30 in between. It's pure cosine law to get the red line. So I'm going to set up my cosine law. Say 2x minus y squared equals one side squared, other side squared, 2 times those sides, cos of the angle. I may need a calculator here, by the way. Yeah. This is going to be 5 minus 4 root 3 over 2. 5 minus 2 root 3, and it's going to be the root of this. Five minus 2 root 3 square root of, please and thanks.
.0935.
2.09 is our magnitude. Okay, so we have our magnitude. And now we want to find its direction. Well, how do I find a direction? Okay, there's no it's not a compass, there's no north heading. So anytime we're given the task to find direction and we're not given really a place in space to direct from, we can direct according to another vector. So I can say, well, I know 2x minus y is this amount of degrees away from vector x. So I can find this angle over here, or I can find it down here and direct it with y. So I can just do this and say, well, if I find this angle I can then give it direction according to x. I can say it rotates clockwise from x. Okay, and if I have all three sides of this triangle and this angle, this is sine law. So I can use this angle with the 1 and the 30 with the 2.09. So I'm going to say over here, I'm looking for an angle, so I start with sine. Sine of theta over 1 equals sine 30 over 2.09.
Sir, sorry, there's a mistake.
Where?
That was in radians. It's 1.239.
Thanks. In radians, what do you mean? Why does that matter? You did the first step?
No, I did cos. I had cos 30 in my equation when I plugged it.
Okay, so from here, to find theta, I have to do sine inverse of sine 30 over 1.24. Remember, for special angles, if we know 30, 60, 90, this is a 2 root 3, 1. Sine of 30 is 1 over 2. So I can change that to a 1 over 2 over 1.24. Keep the sign here. So theta is 1 over 2.48. Doesn't really matter. Sine negative 1 of that. Makes no sense to go here. Just do it from there. And calculate me.
$23.77.
Okay, so I know this angle is 24 degrees. So my therefore statement can now be, well, now I know the direction of vector 2x minus y is 24 degrees rotated clockwise from vector x. Okay, and now I can write it as a vector because it has a direction, the 24 degrees. It kind of sucks to give your direction according to another vector. We like, compass directions, 360 degrees, north of east, stuff like that. But that's what we do. Okay, unit vectors. Took me a while to understand really what a unit vector is, even though it's really straightforward. But it is literally just the number of 1. But because we're multiplying by a vector, this value and this value are going to be the same, right? But this is just the magnitude down here. And if this vector has the information of a direction, all this is a value of 1 that includes the direction in vector x. Okay, so it's really useful to use unit vectors to change something and redirect it into the way that I want without changing the value. So if we're given that the magnitude of vector u is 4 and the magnitude of vector v is 5 and the angle between is 120, determine the unit vector in the same direction as u plus v. So first I gotta find u plus v, whatever way I want to do that. I can make my parallelogram. Call this 60, and this is u plus v. Okay, so I put v over here. I put u over here, head to tail, and then that is my addition. This is u plus v. Okay, so I'm going to do the same thing. It's cosine law with the 60. I'm going to say u plus v, okay, the magnitude. I know the magnitudes of u and v, so it's 4 squared plus 5 squared minus 2, 4, 5 cos of 60. That's 16 and 25 minus 40 times a half. That's 41 minus 20. 19, root 19. Somebody? Root 19.
It's 21, so 41 minus 20.
Thank you, sir. Let's just keep it as root 21. Why would we change it? Okay, so the magnitude is root 21, which means if I want to find the direction as u, put this in the same direction as u plus v, I just have to multiply it by 1 over root 21 u plus v. Okay, scratch that. Once we know the magnitude, we can then say if we want to put it in the same direction as u plus v, I can use this and say, well, this is going to be 1 over root 21, which is the magnitude of u plus v, times the vector that we're using. That's a 2. And I don't know what the direction is of u plus v. I can find it, but I don't care. I can just put it in the same direction as u plus v by multiplying by that vector. And I can multiply this inside, and I can say, well, that means this is u over root 21 plus v over root 21. And this is a unit vector in the same direction as u plus v, because if the magnitude of them is root 21, this is going to turn into a 1, but it's going to go in the same direction as u plus v, whatever the direction is. Okay, so as time goes on, unit vectors play a huge role in like chapter 7, chapter 8, just to like fix a direction onto a vector, okay, that we don't really need to know.